All right, so this is a graph showing the solar energy production from my roof today. I have a 5 kilowatt array, and is a kilowatt energy or power?
Energy.
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 It's not. A kilowatt is power. Remember, a kilowatt hour is power. And so to get energy, you take power and multiply it by time. So kilowatt times an hour equals a kilowatt hour of energy. And so you can see that on this graph, we have, let me zoom in on it. We have kilowatts on the y-axis. And so that's power. That's how much power is being generated. And on the x-axis is time. And so the sun came up at 7. It takes a little bit of energy to actually run the inverter, which converts it from DC to AC power. And so it doesn't really start generating electricity until the sun's quite a ways up in the sky at 9 a.m. in this case. And here it's generating 0.12 kilowatts. And so if it did that for an hour, it'd generate 0.12 kilowatt hours because it's 0.12 kilowatts running for an hour. If it did it for 2 hours, it'd generate 0.24 kilowatt hours. But then as the sun gets higher and higher, and the incident angle on the solar panels is more direct, more perpendicular, it starts generating more and more power. Sorry, my camera is off. Or decided not to focus anymore. Let's try this. And so it generates more and more power until about high noon. It's a little different because of time zones, right? We're not exactly in the center of our time zone, and also because of daylight savings time. And so it peaks around 12:30 in this particular case. And now it's continuing to decrease over the course of the rest of the day. And so each one of these squares represents a kilowatt hour of energy because it's 1 kilowatt tall and 1 hour long. A kilowatt multiplied by an hour, energy equals power times time. So power times time yields a kilowatt hour. And so I can see here I've generated, 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half, 10, 11, 12, 13 some odd kilowatt hours today. And let's check out the actual production. We're at 13.94. So the math checks out, right? Energy equals power times time. And this is a good day for September, so I'm happy. All right, let's get to the lecture. Zoom, fighting Zoom, fighting Zoom. That's the screen I want. Okay, blow that up. And let me get the chat open again. Chat, where'd you go? Just click it over and over again, hoping it'll show up sometime. I find if I share the actual PowerPoint instead of the whole screen, the chat appears more frequently. There we go. All right. Okay. So I can see most of your faces. I can see the chat. Let's do this. So we're going to talk about gadgets and food today. So we're still on our personal energy use journey. How much energy do you use in your daily life? And then we can scale that up to society. Then we'll learn about how society is powered and how that leads to some inequities and how it leads to environmental harm. And then finally, and towards the end of the class, we'll look at solutions to both those problems. So you can't really talk amongst yourselves, but you can sure use the chat or just speak out loud if you'd like to. But are you a terrible person for leaving your cell phone charger plugged in? So I have a teeny little charger next to my bedside table, and it's just plugged in all day long. My phone's charges at night. And so I want you to ask yourselves, are you a terrible person for leaving that plugged in? Maybe.
Wait, is it depend on whether or not you have it plugged into a like plug strip or not?
A little bit, yeah. That has a little light on it and it has a little bit of warmth. So we know there's some energy going somewhere. I'm seeing literally worse than Stalin. That's very much a possibility. No, it doesn't consume much power at all. Not really, but it does use energy wastefully. Isn't it just an extension of the normal circuit now? Yeah, so you all basically get it. That little teeny light on your power strip, that's burning probably like half a watt, doesn't matter. The modern day cell phone chargers that come with like your Apple or Samsung phone or whatever, they even have kill switches, so they're usually just doing 0. My iPad charger draws like maybe 0.5 watts. When your phone's plugged in, it's pulling like 15 to 85 watts, depending on the charger, because it's actually charging the battery in your phone. But when it's just sitting there, nothing's plugged in, it's not that big of a deal at all. So no, you're not a terrible person for leaving these little chargers plugged in. There's some things that if you leave plugged in will begin to consume a lot of energy. And so if you're away for the weekend or a week or something, you may consider unplugging them. We'll get into it. Xbox. Yeah, Xbox is a bastard. It just consumes a lot of energy when it's sitting there plugged in. All right, so let's look at this. This is a couple years back, but there's this BBC, British Broadcasting Company, don't get excited, expose about vampiric devices. So these so-called devices that use power, use energy without providing a useful service to you. And so they found that 65% of consumers leave phone chargers plugged in. On average, a cell phone charger draws 0 to 1 watts when plugged into a wall while not charging a phone. And so we can figure out how much energy this consumes. Remember, energy equals power times time. So 1 watt, let's convert it to kilowatts. So 1 kilowatt equals 1,000 watts. Remember, we're trying to cancel the unit we're getting rid of and find an equivalency with the unit we want. We want kilowatts, so we find an equivalency. 1,000 watts equals a kilowatt. Cancel the watts, and now we have 0.001 kilowatts. And then we multiply that power by time. And in this case, it's 24 hours a day because we leave this cell phone charger plugged in all day long. And so it consumes 0.024 kilowatt hours per day. Not a ton of money. Remember when we made coffee on Friday? I mean, ton of electric energy. When we made coffee on Friday, it took about 0.04 kilowatt hours. So it's about a half a cup of coffee worth of energy, or a little less than like a quarter of a cent. Okay. So daily energy use per person is about 200 kilowatt hours per day. This is over everything: driving cars, shipping packages, energy embodied in all the stuff we have, like chairs and computers, whatever. And so this constitutes about 0.01% of your daily energy use. Does not matter at all. So don't feel bad. You're not a horrible person if you leave your cell phone charger plugged in. Let's compare it to something that does use a lot of energy: moving 1.5 tons of aluminum and plastic around, driving a car. So if we look at a typical car, a Honda Civic, it's like 135 horsepower. You're not generating 135 horsepower of power because you're not flooring it everywhere. Unless, I don't know, during coronavirus, I've been seeing some crazier drivers lately, so nobody's on the road. But in general, your car is much less than that. You're burning about 40,000 watts when you're accelerating. And so accelerating for 1 single second, power times time equals energy, is the equivalent of leaving your cell phone charger plugged in all day. So driving a car for 1 second equals the amount of energy of leaving your charger plugged in. So if you really want to save energy, carpool, ride a bike, walk, don't worry about your cell phone. So this is classic, like, I'm not being a conspiracy theorist or anything, but this classic like media getting, clickbaity and riled up about something, leaving your cell phone charger plugged in when they completely miss the entire point. And that's, what actually consumes energy in your life. It's your heater in your car and flying an airplane. Okay, let's look at some more vampires. So here is phone charger, less than 10 watts. Desktop computer in sleep mode can be 10 to 20 watts. Laptop computer in sleep mode, they're getting a lot better. They're down to like 5 watts. You can tell by how many JPEG artifacts are in this picture that it's a little dated. LCD computer display, about 1 to 3 watts. So that's your TV too. What is vampire power? It's power that a device is consuming within your house that's providing no useful service to you whatsoever. So I have a TV in the other room. It's plugged in. It's off, but it's pulling like 1 to 3 watts, just sitting there waiting for a remote to click it on. CRT, nobody has these anymore. Those are the old-fashioned heavy TVs. Set-top box, digital cable with DVR. So this is like your Comcast box if you actually have cable. I don't know who has cable anymore. Nobody in my generation or yours. So it's super vampiric. It's pulling like 45 watts. Why? I mean, you know that it is. I don't know if you've been to your parents' house or something and you put your hand on it and it's warm, right? Or the cat's always sleeping on top of it. And that's because it's generating a lot of waste heat. The reason is Comcast does not care about you. They will sell you the cheapest, worst, components ever, and then they'll charge you $10 a month for the privilege. And it's garbage electronics that have poor components that waste a lot of energy. And it's not just Comcast. I know I'm throwing shade their way, but it's generally any corporation that is selling you a service, not necessarily a product, and then the product usually suffers. Routers, yeah, routers are bad. Same reason. If you buy a nice router, you'll notice that they run a lot cooler and they use less power. So I have a mesh system in my house, 3 different routers. They each pull about 60 watts each. Not bad at all. Yeah. But don't worry about that. You need the internet on, so you got to keep it on. So here's game consoles. Like Xbox is worse than PS4, which is quite a bit worse than a Switch. But we'll talk about that in a second because information is energy. What else do I want to say about this? There's different new smart home ideas. So this is when we'll get into, solutions to some of this. In a lot of hotels in Europe, and yes, I'm showing my privilege right now talking about hotels in Europe, but you can, as soon as you walk in, when you put your key in you open the door and you put your key next to the wall, a card, and it turns on the AC, all the lights, everything in the hotel. Otherwise, the room is completely dead of power. And so, simple devices like that, which are binary on or off, could be really useful in saving some of this vampiric power because it does add up when you start considering all these different devices. Back before I had 2 little girls running around my house, I had a big kill switch for my house that I would turn off, and it'd turn off the router, the modem, a bunch of other stuff whenever I left the house, just because I was a nerd. And I quit doing that one day because one day I came home and my wife was like, we don't have internet. And I was like, oh, you need to flip this switch and it turns on everything. And she goes, yeah, but I tried that. It didn't work. And I was like, okay, well, yeah, you just maybe turn it on again or check the router. And she's like, I want the internet to be on. Okay. And I was like, well, I mean, it was on, it just wasn't being broadcast by the router. That was the wrong thing to say. It was technically true, but it was not the right way to maintain domestic bliss. Long story short, I keep my router and modem on now because it's just better that way. Don't be an energy fascist, right? Like, figure out how to promote human welfare and tranquility while saving the planet at the same time. Don't sacrifice one for the other. All right. Here's a huge list of a bunch of different devices, gadgets around your house that consume energy. Here's a couple of interesting things I wanted to point out. Like, obviously you don't have to memorize this for a test or something, but I want you to get a general sense of what takes a lot of power, what takes less power. Notice the thing that takes the most power here. It's the vacuum cleaner at 1500 watts. Why 1500 watts? Remember when I turned the kettle on? Anybody remember how many watts it drew Friday? Yeah, 1375. And so that's about the max that you can pull from an American outlet. The max you can pull is 1500 watts. And usually it's slightly less than that because, the appliances protect themselves and your circuit breaker from getting all the way to 1500 watts. And so if you want to get the maximum amount of heat into your water as quickly as possible, your kettle is going to run at like 1400 watts. Vacuum cleaners need to create a vacuum, which nature really doesn't like at all. You're creating this huge pressure differential. So you need a lot of power to do that. And so it's just going to pull as much energy, as much power. See, I get it confused too, as much power as possible to do that. And so it maxes out at about 1500 watts. So that's, if you see something right at 1500 watts, it's usually making a vacuum or heating water. So, my espresso machine, that runs right at 1500 watts. Vacuum cleaner, 1500 watts. A shop vac, 1500 watts. Chop saw or whatever, 1500 watts. Okay, so that's where that 1500 number comes from. One thing that's surprising when I first started learning about this is how little power is consumed by things like stereos or this is TV, different things like that. Things that produce information for our senses. So light and sound are generally pretty low watt things. And it's because we evolved on the savannah 250,000 years ago, and we were largely nomadic and nocturnal, and we only run at 100 watts ourselves. And so our senses are designed to see basically in the dark. We're designed to hear predators far away so that we don't die. Evolved to do all these different things. And so we have incredibly sensitive senses. They don't require a lot of energy for them to work. And so you don't want to blast your ear holes or eye holes with, over 100 watts, or it's painful. And so this is why these things actually don't take that much power. Okay, last thing I want to talk about is video games, because I'm a nerd. We have Xbox, PlayStation 4, and Switch. PlayStation 4 has slightly better graphics. It's slightly more powerful than the Xbox One, and it uses slightly more energy. And that's because arranging all that information together takes energy. You're fighting the natural order. The natural order is for things to just entropically disperse and scatter and become less and less ordered. And so to maintain that order, that information fidelity, you need a lot of power. Now, the Nintendo Switch is a totally different beast because it has a much smaller processing power, and they focus more on other things besides raw graphics, and so it takes far less energy to produce the same experience, I guess. So that's just something. And the more powerful a computer is, the more powerful a graphical processing unit is in a computer for a given generation, because yes, there's efficiency gains with each subsequent generation because things get smaller in the chip architecture. Then you use less and less. The more powerful it is, the more energy you're going to need, the more power you're going to need. Okay, the rest of this stuff is boring. Nobody has an answering machine, I hope. Okay, so in summary, your computers and entertainment systems are the greatest energy consumers among your gadgets. But gadgets as a class don't consume that much energy. Things like cars and heating your house, that consumes far more energy. Lighting consumes about 4 kilowatt hours a day. And that's for mixed lighting. If you have just LEDs in your house, you're going to be down to like 0.4 kilowatt hours per day. On average, people consume about 5 kilowatt hours a day using gadgets, phones, computers, vacuum cleaners, whatever. So the moral of the story is don't be a fascist with your gadgets. Don't follow my example. But if you do want to go on vacation for like a week, shut some things off, unplug some things. It's not doing anything for anybody. All right. Let's move on to food. Let me look at the chat, see if I missed anything. Yeah, switches, rad. Rip the new NVIDIA GPUs. Yeah, those are going to be very energy intensive. You have to buy a whole new power supply unit for your computer if you want one of those. If you can actually find one. All right. Food. Recall a vegan consumes about 5 kilowatt hours per day, and a paleo dieter consumes about 20 kilowatt hour per day. How exactly did we arrive at these numbers? So this, I'm basically just going to walk right through McKay's chapter on food that's linked below this lecture. Okay, so how much energy does it take to maintain a human? So you are a chunk of flesh, mainly water, and you are at 98.6 degrees Fahrenheit. And that is different than the environment around you. And so you need to put energy in you to maintain that temperature gradient. Just how much you need depends on your activity. If you are doing more than just maintaining your temperature, if you're walking, if you're running, if you're exercising, lifting something, then you're going to need more energy. And if you have more flesh, because you're a bigger person, a stronger person, etc., then you will need more energy. An average person requires 2,600 kilocalories, which is a calorie in American language of food. It's a lot of energy. It's 4,100 joules. If you want to find out your exact dietary needs, then you can click this link here, and it asks you about your weight, your height, your sex, and your level of activity. And it'll give you the amount of energy you need to maintain your current weight. If you want to gain weight, then you'll have to eat more than that. If you want to lose weight, you'll have to eat less than that. It's just simple thermodynamics. Energy in equals energy out. And if you have more energy than you have out, you're going to store that energy. Otherwise, it's the other way around. Okay. So how much energy is that in terms of kilowatt hours? We need to convert from this energy unit, kilocalorie, to kilowatt hours. So we have 2,600 kilocalories a day. Trying to get rid of kilocalories. And replace that with joules. We know that 1 kilocalorie equals 4,184 joules. This is an equivalency. So we multiply that together. Kilocalories cancel. Now we're left with joules per day. And now we convert that to kilowatt hours and recall from Wednesday and Friday that a kilowatt hour is 3.6 million joules. It's lifting an apple from the floor to a desk 3.6 million times. And once we run through these two conversions from kilocalorie to joule and joule to kilowatt hour, we find out that a human takes 3 kilowatt hours per day. If we wanted to get our actual wattage, well, energy equals power divided by time. Power equals energy divided by time. So then we would take kilowatt hours, which is energy divided by time, 24 hours a day. And you'd realize that humans only consume about 0.1 kilowatts or 100 watts of power. So we're very low. We don't demand a lot of power. We're very efficient. Okay, energy for food breakdown. So say you consume a pint of milk per day. If you don't drink milk, you may consume it in other forms. You may have cereal, you may have a latte, you may have ice cream, you may have chocolate or cheese. So a typical dairy cow produces we're trying to figure out how much energy you actually need to maintain your diet. Typical dairy cow produces 16 liters of milk per day. A liter is about a quart, and a quart is 2 pints. So this is 32 pints. And recall, you consume about a pint a day, and a cow makes 32. If you eat cheese, it's very milk intensive. It's just dry cheese. Cheese is just dry milk. It's, some bugs or enzymes or something eat all the sugar and get rid of all the water, and it makes a chunk of cheese. So to make 1 kilogram of cheese, you need 9 kilograms of milk. So if you eat 50 grams of cheese, which would be typical in something like a sandwich or an omelet, you need another pint of milk. So now we're up to 2 pints of milk per day per person. And so now we need to figure out how much energy we need to maintain a cow to provide you with those 2 pints of milk. Cows and humans are the same thing. We're both mammals, right? We're both run at about 98.6 degrees Fahrenheit. Cow is just bigger. We take 3 kilowatt hours per day to run, And a cow is 7 times larger, so they take 21 kilowatt hours per day to run. Actual measurements are about 24 kilowatt hours, but you can see the power of just simple, ratio and proportions, just thinking about things and generalizing. So a cow is 24 kilowatt hours per day to run, and they make 32 pints of milk. So 24 kilowatt hours per day multiplied by 1/16, that's how much milk you consume. So if you consume dairy products, we need another 1.5 kilowatt hours for your personal energy budget. Struggling to keep up. Yeah, I ran through this math pretty quickly. Basically, it's how much milk do you use from a cow and how much energy does it take to keep that cow alive, to give you that milk. I'll be around after class if we want to go through it more slowly. Note that this ignores all the life cycle costs, all the upstream costs of actually milking the cows, making the cheese, shipping the milk, refrigeration, all those sorts of things. So it's good. This is a minimum. Okay, now let's say you eat eggs. So a layer hen eats about 110 grams of feed per day. They lay about 290 eggs per year, 365 days per year. So this is a little less than 1 egg per day. It's 0.8 eggs per day. And you need to put energy into that chicken, right, to make it work. So chicken feed is 2850 kilocalories per kilogram. And so it's about 3.3 kilowatt hours per kilogram of feed. How much does a chicken eat? A chicken requires 110 grams or 0.11 kilograms. Sorry about the units here. And so it's 0.4 kilowatt hours per day. So chicken makes 0.8 eggs per day, and they require 0.4 kilowatt hours of feed per day. And so if you divide that eggs per day over kilowatt hours per day, the days cancel, and we realize that 2 eggs are generated for every kilowatt hour of energy you put into a chicken, right? It's a factory. You put a kilowatt hour of energy into the chicken and 2 eggs come out the other end. So how efficient is this factory? Let's think about it. All right, switch cameras. There we go. All right, that doesn't look good. All right, and let's put on video mode so you guys can actually see some things. Let's get it in focus. Okay, that was from the other day. Okay, so far you've seen 2 equations in this class. Power equals energy over time. You've also seen the heat capacity equation. I'll write it down here, but we're not going to use it in this instance. If you want to change the temperature of something, how much energy you need depends on how much mass you have, the heat capacity of that stuff, so its propensity to change temperature with an energy input, and how much temperature you want to change that material by. Okay, well, we're talking about chickens here. So chickens are a factory. I draw all factories like a coal plant. You put 1 kilowatt hour of feed into that chicken, and out comes 2 eggs. Okay, so we know these eggs have 70 kilocalories of energy. When you eat an egg, you get 70 kilocalories. So 70 kilocalories per egg. And we know from the feed analysis from the chicken that 1 kilowatt hour makes 2 eggs. Okay, I already stated that. Sorry, let me think for a second. It's hard to talk and do math at the same time. So what we want to figure out is the efficiency. So we know that the efficiency of something, and this is the third equation I need you guys to know for this class, of about 4 equations total. This symbol is eta. It's a Greek symbol that physicists use for efficiency. I don't know why, but that's what it is. So efficiency equals energy outputs over energy inputs. I spent a lot of my youth in Oregon, so I'm a little more colloquial. I just say what you get over what you pay. So in the case of this chicken, you get 2 eggs, and that's 70 kilocalories per egg. And I won't go through this conversion, but 70 kilocalories is point.
I'm sorry, sir. What's the number that you put on top of egg?
70 kilocalories. It's a 70. So this is what we get. We get 2 eggs, and there's 70 kilocalories per egg, and there's 0.04 kilowatt hours per 70 kilocalories. And I'll explain why I'm doing these conversions in a second. And the energy input is simply 1 kilowatt hour. So I'll take a little break for a second to explain things. When you do this efficiency calculation, it's always less than or equal to 1. You don't get things above 100%. I mean, you can with different coefficients of performance, but that's for a later class. And for this notation to work, the units of these 2 energy terms need to be the same. So it needs to be joules over joules, or kilowatt hours over kilowatt hours, or megatons of TNT over megatons of TNT. Doesn't matter. It just means that the units of this term, eta or efficiency, are dimensionless. The units cancel. And that's why you can relay it as a fraction or a percent or a number less than 1. You're trying to figure out what percentage of your energy that you get out is a fraction of the energy that you put in. And so I ran through these conversions to get everything in terms of kilowatt hours. So I have kilowatt hours over kilowatt hours, energy over energy. So the eggs cancel, kilocalories cancel, and now I have, and this 70 cancels. Now I have 2 times 0.04 kilowatt hours. And this is kilowatt hours over kilowatt hours. So if we crank through this math, we see that, sorry, I'm trying to straddle this camera here, is 0.08 over 1 equals 0.08. And so this equals 8%. So that's the efficiency of a chicken. I may have dropped a factor or two in there somewhere. The point is that this chicken is okay. You put in feed and you get eggs out, and it's somewhere at the level of like a really crummy solar panel, and that kind of makes sense because it's taking energy, and it's focusing most of that energy on maintaining its own body temperature and flapping about and doing chicken things. It's not so concerned with making that egg, and so only 8% of that energy actually goes into an egg. It's actually really impressive when you look at how much energy a lot of things put into general reproduction. I guess humans put in a ton of energy if you're female for 9 months. Males, I don't think, put in a lot of energy at all. Okay, let me check this chat. Can your next calculation be about how much energy it takes to make pancakes and how much energy you get when you eat them? Yeah, that actually is probably pretty efficient because all the energy is just in the sugar, the syrup. Yeah, I can mess around with that. Not today, though. All right, let's switch back to the slideshow. Okay, share screen. Is still sharing. All right. Was that camera full screen when I was doing those calculations, or were we still on PowerPoint? Camera was full screen? Okay, good. I was worried you were seeing a teeny little corner in the side. Okay. Meat. What time is it? 2:36. Okay, good. This is all from McKay's book again. So he's a physicist like myself, so it's pretty quick and dirty calculations. The actual results are probably off by, factor of half or so. So you eat 1/2 pound per day. So this is for meat eaters. So say you have, a little bacon at breakfast, turkey sandwich at lunch, and, hamburger for dinner or something. It's a lot of meat to eat in one day, but say you do that. Then you need to keep animals alive. So chickens mature at 50 days. And so you must maintain 25 pounds of fryer chickens alive. So this is if you're eating 1/2 pound of chicken a day, then somewhere in Skagit Valley, you need 25 pounds of chicken, walking around, or more likely trapped in a cage somewhere, to satisfy your dietary needs. Pigs mature at 400 days. And so you must maintain 200 pounds of pork somewhere on a pig farm, meaning that like every day, some pig will be slaughtered and 1/2 pound of that pig will go to you. And for all the other parts of the pig that are going all everywhere else, someone needs to be maintaining 200 pounds of pig somewhere for you to have that 1/2 pound of pig per day, because you can't just take a 1/2 pound of flesh off a pig. It's not good for it. Cows mature at 1,000 days, so you must maintain 500 pounds of cow if you're going to eat a 1/2 pound of beef every day. So it's quite existential, right? The amount of energy required for you to satisfy your meat habits depends on how long it takes to bring that animal to maturity. So say you eat 1/3 of each, so a third of a 1/2 pound, 1/6 of a pound of chicken, 1/6 of a pound of pork, and 1/6 of a pound of cow over the course of your day. Then you need to maintain 8 pounds of chicken, 70 pounds of pig, and 170 pounds of cow somewhere. So this is 110 kilograms of meat, or 170 kilograms of animal. So I took 170 pounds, converted it to kilograms, and animals aren't pure meat. We haven't got that lab grown meat quite yet. So there's other parts of the animal that you don't eat. And so you actually need to maintain 170 kilograms of animal to satisfy your meat habits. How much does it take to maintain an elephant? Well, we can look at that. You would put in the mass of the elephant right here. So you'd put in, 1,000 or 2,000 kilograms. But let's stick with the stuff you actually eat. 170 kilograms multiplied by 3 kilowatt hours per day over 65 kilograms. What's this 3 kilowatt hours a day and 65 kilograms come from? Where did I pull those two numbers from? Humans, yes. So I'm setting up a ratio and proportion going from livestock to humans, because this is something we know. This is something I know. I know that I take 3 kilowatt hours per day and I weigh 65 kilograms. So I can set up this ratio and proportion and convert animal mass to human mass and then relate that to human energy needs. So because this mass is greater than 65, it's going to require more energy to maintain this mass. And if it was 1,000, like an elephant or something, it would take far more. And so to maintain this 170 kilograms of livestock, you are indirectly consuming 8 kilowatt hours per day. So somewhere, chicken farm in Skagit Valley and a horrible beef lot in Bakersfield, California is burning energy to satisfy your dietary needs. Sorry if you're from Bakersfield. All due disrespect, I'm glad you're in a better place now. Okay, so is this an argument for vegetarianism? If you just live off vegetables, it's only 1.5 kilowatt hours per day. If you add milk to your diet, that's 1.5 more kilowatt hours per day. If you add eggs to your diet, that's another 1 kilowatt hour per day. If you eat meat, that's another 8 kilowatt hours per day. If you're pure paleo diet, then it's like 20 kilowatt hours per day. So is this an argument for vegetarianism? And that's a loaded question. So maybe a better question would be, under what agricultural practices might a meat-based diet might make more energetic sense when it's not such a good idea? This is why water is the best. What about grains? Grains are vegetables, or the plants. Hunting. So yeah, that's an interesting. Grains are actually kind of intensive because they require a lot of fertilizer. Hunting. Yeah, corn ethanol actually is energy negative. It takes more energy to make corn ethanol than you actually get out of it for your car. It's just a big energy laundering scheme, money laundering scheme for the Midwest. Anyways, let's not say things that get me fired. What about grains? Hunting it's a good argument for hunting, but obviously we can't all hunt, right? There might not be enough calories available. It might not be sustainable, except on campus. It seems like there's deer everywhere. I guess you could just like choke out a deer if you wanted to. Water and vegetables and fish. Fish is a very interesting one. So that doesn't take any energy because the sun and the algae and the phytoplankton and the ocean is providing the energy for us. It takes energy to run diesel in the boat to go out and get the fish, but nearshore fish, like herring, don't take much energy at all. Squirrels, raccoons. Yeah, so you noodling, you guys get the idea, right? So there's certain circumstances where meat-based diet, don't feel bad if you eat meat, right? But understand that there's different practices that are more energy intensive and less energy intensive when it comes to meat consumption. So meat isn't the best for the planet. It consumes a lot of energy. Cows in particular emit a lot of CO2. I'll get into that in a second. And so one thing I've chosen to do personally, and you don't have to follow this at all, is I'm much more selective about my meat consumption. I treat it like a treat, right? Something that I enjoy with family or friends on rare occasions, right? You guys are too young for this, but it's like, a dram of scotch. You should not have it every night. It's going to be bad for you. Okay. What's a dram? It's a relative measure of whiskey. So you can have a dram or a dram, depending on how much you want. It's a way to not get judgy about your scotch consumption. Okay, so this shows the energetic efficiency of food. So we looked at the chicken, and the eggs were We measured 8%. The real answer is 11.2. So our back of the envelope calculation was pretty good. That was just based on, thinking about humans and chickens and things like that. The most efficient foods: herring, corn, soy, apple, potatoes. How did they get above 100%? I just told you you can't get above 100%. How did these foods get above 100%? What are the energy inputs here? Free energy. Yeah, it's free, but where does it come from? The sun. Yeah, so we're getting this free energy from the sun. Herring indirectly, right, with the phytoplankton and algae they eat. So the farmers didn't have to pay for a lot of these energy inputs that yield these big energy outputs. So some of the least energy efficient things are shrimp. I don't know why. What's this one? Lamb. Yeah. This stuff is all sad when you start thinking about it, right? It takes a lot of energy to maintain these animals, and a lamb doesn't yield a lot of meat. It takes a lot of energy to maintain adult sheep to make lambs. Anyways, let's not get into sad subjects. CO2, this is interesting. Carbon intensity of food. This is the column of merit, emissions in grams of CO2 equivalent per kilocalorie of food. So what is the worst food for climate change? The answer is beef. That's because beef burp a tremendous amount of methane, and methane is a very intensive greenhouse gas. It's 25 to 100 times more intensive than CO2. So if you put a kilogram of methane in the atmosphere, it's like putting 50 kilograms of CO2. So beef is a big problem for climate change because of their vast quantities of methane that they produce. It turns out you can feed them a little bit of seaweed and it stops the methane production. But seaweed's expensive to feed to cows, right? So not everybody's doing that. Nobody's really doing that. So again, eat beef more selectively if you're concerned about your carbon footprint. Okay, what time is it? 2:46. We got 4 minutes. In summary, about 12 kilowatt hours of your 200 kilowatt hours of personal energy use per day goes into food. A little bit goes into fertilizer. Fertilizer is basically natural gas. We'll talk about that later. Some farm equipment, about 15 kilowatt hours in total. If we look at total U.S. energy budget, about 6% of U.S. energy budget goes to food. 300 years ago, how much of a society's energy budget do you think went to food? Most of it, a lot. Yeah. Yeah. So most of us would have been peasants or villagers, or depending on where we lived or whatever. And we would spend all our day using energy to make food. We'd even make food energy for our animals to make food energy. Like we grow hay to get a cow to plow a field to grow corn or something. And so most all of the energy just went to food. And that's why things are pretty amazing right now. We don't have to spend that much energy making food. So we have all this extra energy for all these wonderful things like Zoom lectures. What about if you have dogs and cats and stuff? Well, we can scale it all to humans. Cats are not 2/3 of a human, but they still take 2 kilowatt hours per day. That's because they're crazy. They spend a lot of extra energy doing silly things. Same with dogs. So these are much more energy intensive animals than us. They run hotter than us. Their body temperatures are higher. Horses are huge, so they take 17 kilowatt hours per day. And you can start to almost look at little trends, right? What is personal wealth? How does personal wealth correlate with these different pets? Right? It costs some money to have a cat. It costs a lot more money to have a dog, and it costs a ton of money to have a horse. We'll see that energy use completely scales with wealth. And the crazy thing about energy is it's insatiable. Like the more wealth you have, the more energy you can burn. to the point where you're like Richard Branson or Elon Musk and you want to build rockets. Okay, last slide. Energetics of losing weight. If you're concerned with these topics, when we consume more calories than we burn throughout the day, our bodies convert that into fat. This is an amazing adaptation of evolution. It allows us humans to not eat for like 30 days. So it's this incredible adaptation we evolved with during times of scarcity 10,000 years ago. It's a problem now because we don't have scarcity. Human fat is adipose tissue or animal fat. It's a bunch of carbons, even more hydrogens, and some oxygens. This is the molecule for fat. And so when we burn fat or we metabolize our food, we combine that fat with oxygen that we breathe in, and then we breathe out CO2, and we also breathe out sweat or urinate water. And so this is how we actually lose weight. We burn the fat chemically within our bodies with oxygen. So the only way you actually lose weight is by breathing it out. You don't lose weight by, people think other bodily functions are causing them to lose weight. That's just getting rid of the waste food. So if you want to lose weight, you got to breathe more. So that means exercise. You can't just hyperventilate because then you fall asleep and breathe slow again and it equals out. Or you stop putting less food into your body. So it's awful. I wish there was a trick to dieting. There isn't. It's just thermodynamics. It's more true than death and taxes. The only way to lose weight is to put less energy in or put more energy out. So yeah, this is fat, this is air, this is your breathing, this is water. And this arrow, I have no idea what happens. You have to have like a PhD in biochemistry. And this is where different things like metabolic rates and different thyroid conditions and et cetera can complicate this basic thermodynamic structure. All right, I'll hang out for the next 10, 15 minutes if you all have any questions.
Sir, could you give us can you give us a little bit of help on how to do the homework before we turn it in next Monday?
Yeah, Friday we'll have an entire study session that I'll post to YouTube, so it'll be available for review all weekend long.
Is there any information in the book that could help us?
Absolutely. In the homework itself, I reference a chapter, a heating chapter for the shower and bath energy consumption calculation. And if you go to that chapter, the homework should be very straightforward because I took it from that chapter. But again, we're spending the entire day Friday together working on the homework. We're going to do that for all the homeworks because of the online nature of this class. I can't sit in my office all day long and help you all whenever you care to stop by. And I'm certainly not going to sit on Zoom all day long. So I've decided to concentrate that time into class scheduled study sessions.
Okay.
Hey, Professor?
Yes.
Could you go back like 3 or 4 slides? I was trying to ask a question and then I realized that my mic wasn't working.
Yeah. This one or further back?
A little further back. Like 2 more, I think. Even more. Yeah, right here. Where are you getting the 170 kilograms from?
Yeah, I glossed over that really quickly. So say you eat 1/3 each, 8 pounds of chicken, 70 pounds of pig, and 170 pounds of
Yeah, it's pounds.
cow.
Why is it going to kilograms?
Yeah, so I skipped a step because I ran out of space in PowerPoint. So if you add 170
times 2.2, and then you could do kilograms. Oh wait, never mind. It's kilogram. So you divide by 2.2.
Yeah, 110 times 2.2 is what, like 250 or something, and that's what 170 plus 70 plus 8 equals. So I added up 8 pounds plus 70 pounds plus 170 pounds. Divide that number by 2.2 because that's the conversion from pounds to kilograms. That yields 110 kilograms of meat. That's what you eat, but an animal isn't pure meat. So you have to scale that up to 170 kilograms to account for things like bone and guts and stuff.
All right.
I glossed over a lot right
about
here.
170. Right. That's all I needed to know. Thank you.
And this is all ripped from McKay's book, and it does a great job explaining it all.
All right, all right.
One question.
Thank you much.
Yeah.
So if you're having problem with the with like figuring out how to do the work by yourself, you just want to practice, can we like email you? Do you have like
Yeah,
a
by all means. Yeah, email me. I'll be sure to answer it. And yeah, the book is an excellent resource too. But yes, I'm happy to work together over email, and then yeah, especially in Friday's study session.
all right, thank you.
Yeah, don't be a stranger. In one of the lectures this week, could you go over what material will be on the test and what to expect? We'll definitely have like, personal energy use equations. The most important one is power equals energy over time. I'll probably have a question to do with heating water, and I'll probably have some general questions about, how much energy goes into food and that sort of thing, more qualitative stuff. And again, the test will be open book, open notes, and over the span of days. So it should be pretty low pressure. Once I write the test, I'll be able to answer that question more accurately, but I will pull questions from these lectures. Is the test timed? Haven't decided yet. I don't really like the nature of tests personally, and I understand people get test anxiety, and so I don't like 1 hour tests or something like that. So I'll probably release the test and give you all like 2 days to turn it in, or 3 days to turn it in, something like that. And just don't be a cheater, right? It's obvious when people cheat, and you'll be punished if you cheat.
How can you cheat if it's open book?
When you have the exact same answers as another student, especially when it leads to the same wrong answer, it's obvious.
Didn't realize you could hear me.
But yeah. Anything else? Yeah, don't be shy with questions. It's only day 3. We got time to figure this all out.
Thank you, Professor Barnhart.
My pleasure, Tony.
Excuse me, Professor.
Thank
Yes.
you.
Earlier today, you introduced the third of 4 equations that you wanted us to know, and I don't think I caught the second one.
Yes. I'll just write on this slide here. Annotate. Draw. Okay, so yeah, so the first one is power equals energy over time, right?
Yes.
And the second one is the efficiency. The third one is efficiency. The second one is the heat capacity equation, which is a change of energy, let's say in joules. If you want to change the temperature of something, you have to put energy in. How much energy you put in, that triangle means delta or change. How much energy you put in depends on how much stuff you have. So that's kilograms. The heat capacity, and this is in joules per kilogram per degree Celsius or Kelvin. And then the amount of temperature you want to change something by. And since I have Celsius here, I'll put Celsius up here too. So say we have, a kilogram of water and we want to change its temperature by 100 degrees, then the amount of energy we need is, 1 kilogram. And the heat capacity of water, I think, was 4,200 joules per kilogram per Celsius. And we want to change it by 100 degrees Celsius. Then we will need 4,200 joules of energy to lift that water's temperature by 100 degrees.
All right. Thank you.
Yep. Cool. I'm going to peace out. Have a great week. See you Wednesday.
You too.